time, and maybe there are a couple of people still coming. So let's get started, and welcome to this week's High seminar. And today, we're very glad to have Baris Altunkaynak here, and he's going to tell us about measuring masses in Cascade decays with the help of multi-body phase space. So let's welcome the speaker.
Thank you very much for the invitation. We just realized that time kind of runs. Measuring masses in Cascade decays to help with space. Okay, so our goal is finding a new and better method of measuring unknown masses in a decay chain, and at least one invisible particle. So this is not the first step. The first step of this was done in this paper by Untitled and you, and I joined the effort later on, and I think we had a couple of more steps into this. With again John Kulich and his student Matt. Okay, so of this kind of abstract thing of measuring the masses is of course motivated by the current status of the particle physics. Let's see what we know right now about the new physics so far. There is more that we know that new physics is not something more than we know what it is. So far, the only thing the LHC has found is the Higgs boson, or a Higgs boson. We're still not sure. And its coupling, or if you look at the signal strength plot produced by Atlas and CMS, the signal strengths agree very well with standard model Higgs. If there's more than, if there's an extended Higgs sector, we could be in the decoupling or relying on the limit of this multi-Higgs doublet model. But it seems that it's not going to be easy to find the other states looking at this well agreement with the standard model. But at the same time, there were some signs of flavor changing interference. For example, CMS observed some small excess in Higgs to TAMU. And although it's not easy to observe the Xavier states, you can actually see one of them through flavor changing couplings. What about supersymmetry? No signs of supersymmetry yet. And the discussion is if the electric sector is fine-tuned, and depending on how we define it, could be fine-tuned or not so fine-tuned. And with some type of definition, you will motivate yourself that you should see lightning xenos, and you might also get some nice signatures from those. But the overall result is, the summary is that if there is new physics around, it's not so easy to find, and if you can see it right away at this 13T we run in the first year, it's going to be much more difficult to see it and measure the masses and couplings if we can actually see it. So we really need some methods that can work with minimum statistics, minimum number of events. Now, measuring masses of new states could be a trivial thing or very difficult thing to do. If we are talking about just visible final state, that's a piece of cake. You just do p squared and you get a peak. So then discovery of new physics is the same thing as measuring the mass. But if there are massive invisible particles, then discovery and mass measurement are completely different things. What are some current mass measurement methods? There's a large number of them, and there's a nice review paper about them. A couple of them are polynomial methods. So if there's enough number of particles in the event along a cascade, and you look at the same type of event, same type of cascade. If there is, you can construct a constraining set of equations by using the invariant masses. And if each event has more equations than the unknowns, that means by adding a couple of events, you can actually solve the whole system. But that requires, for one invisible particle, that will require 5 final state particles. There are some edges and endpoint methods. Again, due to these invisible particles in the events, you get kinematic edges or endpoints when you plot some of the invariant mass distributions. And you can, if you have enough statistics, you can populate them, measure the edge, and usually those edges or endpoints are correlated with the mass differences. And you can measure the mass differences from those and finally obtain the actual masses of the new particles. And if the cascade is not long enough and there is more than one invisible particle symmetric event, you can do something playing around with transverse mass, or transverse mass in this case. You combine two transverse masses and you scan over the unknown two-dimensional missing PT for one of the particles, and from that you can put bounds on the other particle. So let's focus on edges and endpoints, for example. The idea here is to look at one-dimensional projections. For example, if you look at this cascade decay, x going into 1 plus y, and y goes into a 3-body decay with one invisible particle form. So we can form M23 or M123 from these variables from this event, and we will expect an endpoint and an edge. But if you look at this two-dimensional plot, M123 and M23, imagine here's your event. You can talk about the boundary of the phase space in this two-dimensional space, and knowing the boundary and having an event will give you the power of eliminate a bunch of mass hypotheses, which you cannot do by just looking at the projections. So projecting onto this axis or this axis gives you something in the middle, doesn't give you that much power of rejecting mass hypothesis, but you can single out this much of the space by just having an event over there. And as we said before, so this is one of the problems with edge and endpoint analysis. This one-dimensional projection does not capture the whole picture. And also, since you are getting mass differences, it's kind of insensitive to the overall mass scale. Okay, if we go to higher dimensional, higher number of particles, how do we normally deal with this n-body phase space? If we write down the n-body Lorentz invariant phase space, we have this big P over E Lorentz invariant phase space volume element. Normally what we do is when we integrate, we calculate three-level stuff, and if we do Monte Carlo, we usually use phase space reduction. We take this difficult-looking set of DQPs and divide them into sequential two-body phase spaces. And then we have to integrate, each time we do this, we have to integrate over one invariant mass. And that could be a good thing if there's a resonance, and we can eliminate that. But it kind of loses the correlation between, let's say, if you want to study invariant mass of 1 versus 3, since it's going sequentially, it doesn't capture that. So the question is then, how do we use this whole set of invariant masses, or how do we look at the big picture and study the phase space in its full dimensionality?
What do you mean by tangent transformation?
Tangent? Yeah, tangent transformation. Right. Yeah, you can do a tangent transformation if you have a resonance, which will flatten it out, and it makes it especially easy to do Monte Carlo integration. Okay, so there is a way of describing the n-body phase space by using only Lorentz invariants, so pi dot pj's. Over here we were using these DQPs, and then we got two-dimensional product of two-dimensional phase spaces and an integration over EMs. Over here we want to study the whole thing in terms of these xij's, which is pi dot pj. So consider this n-body final state, x goes into 1 to n. Doesn't have to be a direct decay. It could go through two-body, three-body decays, doesn't matter. And we know that spin sum amplitude square can be expressed in terms of xij's, so it's a good idea to look at this phase space in terms of xij's. So the question to ask is, what are the kinematically allowed values for xij's? How do we define the phase space, especially the boundary of the phase space, in terms of these xij's? And another important problem, how do we express the phase space volume elements in terms of these xij's? It was very easy over here. It's not going to be that easy in terms of these variables. And these are not all independent, of course. How do we deal with that? So this question was answered 50 years ago by Baris and Yang. And so let's go over this answer. Now, starting with these xij's, we can do two things. We can define a matrix, right? That's sometimes called as a gram determinant. Each term is pi dot pj here. And we can also define a Cartesian space by using these variables. And there's a connection between these two. And there's a connection of defining the phase space in this Cartesian space by looking at this matrix over there. And that connection is done by looking at the properties of this matrix, especially its eigenvalues and the sign of those eigenvalues. So a number of negative and positive eigenvalues determine everything in this picture. So if you just forget about the pi pj vectors, just I give you a matrix, I ask you, is this coming from an actual event or not? The question becomes just finding the eigenvalues and finding the positive and negative eigenvalues of this matrix. And if we define a region R, A, B, and this Cartesian space in such a way, M and sub n has A positive and B negative eigenvalues, and we do this connection, and it turns out realizable regions, which means physical regions, and this Cartesian space consists of SR1, 3, 1, 2, 1, 1, and 1, 0. So if you think about this matrix again, we have lots of zero eigenvalues. Imagine let's say a five-body final state, right? Our region R1, 3 means there's one positive eigenvalue, 3 negative eigenvalue, and one zero eigenvalue. So in a sense, this matrix is capturing what happens to those pi pj vectors. And since we live in 1 plus 3 dimension, those vectors cannot span larger than 4 space-time dimension. And this 0 eigenvalues captures that. And sometimes, like in the dotted plot case, your vectors get aligned and you don't span 3-dimension or 2-dimension. And then in that case you go down to these smaller regions. So the largest region will be R13. If you don't span 3 space dimension, then you go into R12, which is smaller, so R11, and R10 is finally just a set of points in the singular points in the space space. Okay, now how can we give an algebraic expression of this number of positive and negative eigenvalues? And it's done by just looking at the characteristic equation for the matrix. And we encounter these deltas coefficients for this polynomial. And those coefficients correspond to so-called diagonal minors of this matrix. So imagine the whole matrix. A diagonal minor is just to remove some number of elements from columns and rows, the same number from rows and columns. And a point of Mn is in R1M if these conditions are satisfied. So for each physical point, we need to have these coefficients positive, and the larger ones should be exactly 0. That will set the correct number of positive and negative eigenvalues. Okay, so let's do this for the 3-body final state. That will clarify things a little bit better. The Dallas region. So we construct this matrix M3. And in this case, we have three-body final state. Now the largest region is going to be R12 because it's a 3-by-3 matrix. We're going to have 1 positive, 2 negative eigenvalues, and the boundary of the phase space in this case is defined by delta 3 equals 0. Here over here, I'm plotting exactly that. So delta 3 equals 0 is plotted over here, and the axes are just these x1 to x1, 3, x2, 3 coordinates. Again, those x's are dot products of vectors. Okay. So then, how do we get our usual nice-looking Dallas region? There's one more thing we need to add. If you think about it, this equation doesn't have any mother mass. Right? All the daughter masses are here, but no initial state particle mass. If you add that to the picture, which is just this, you write down a condition for the invariant mass of the mother particle to be equal to the sum of the P1 plus P2 plus P3 squared. You get this condition.
So you are assuming that you would see endpoints for all these decays. That's your assumption.
We will see.
You will see endpoints for all these decays.
Endpoints?
Like S1, 2, S2, these are all endpoints. Like in a decay, you have 1 goes to 2, 3. So you are trying to find all the endpoints and then use this.
Right, we have 3 particles.
Exactly.
We construct all the.
But not necessarily in a cascade. You see.
Right, this is
clearly,
three
just you
body
assume that you'll see the endpoint. Because in realistic scenarios, suppose at the LHC, you have 2 sides, and one side may not be symmetric to the other side,
Right.
and the endpoints may not be there at all, unless you are very lucky. So you're just assuming you are seeing endpoints, and then you are trying to reconstruct it.
Well, so far I'm not doing anything related to
Just you are saying
actual mass
that
construction.
one decay chain, and then
Right. This is just a direct 3-body decay from one particle to 3-body decay. Just to give you an idea of these delta quantities. So again, here's our delta 3 equals 0, these red regions. And this is the energy conserving plane in this 3D. And that cuts this region. And as you can see, here's our Dallas region. actually, we usually, we normally just plot the projection of that region into one of the faces. Okay, then let's talk about the.
You have a plot if the initial state is optional. So you have a plot if your some of the final state momenta are optional. So you imagine the width for some
Oh, what
virtual
about
processes.
this?
Yeah.
Yeah, these are all on shelf.
The triangle you draw is an on-shell particle, right? But if you have a state in which, say, a virtual process, nothing is on-shell, so generally what does that look like?
Good question. Well,
What is it?
so single mass going into 3 offshore.
No, I'm not saying.
Or goes
so
into
for
2.
example, you have a virtual vector boson interaction, decay into
Uh-huh.
vector things. But when you sum up the final state momenta, they don't have an on-shell particle, they just have an off-shell. So I wonder what does this face
I mean,
about that?
I don't know if it will be a good idea to look at this plot in terms of an offshore.
Well, maybe it
You
doesn't
can think
really
about
matter, but,
I guess going through 3-body decay through an offshore, let's say double boson, and that offshore, depending on how offshore it is, it's not going to affect the final.
Oh, for that purpose, it is still somewhere in your phase space, right? It's I'm just saying about drawing this triangle, which is assuming on-shell particle initial state. I'm just wondering if that is, if assumption is not there, how does this change?
I mean, matrix element is not here yet, so
Oh,
it won't
basically-
change anything if there was an offshore, slightly offshore, very offshore, intermediate state. It doesn't matter in terms of the final state configuration right now, because we are just looking at the phase space. We are not looking at the matrix element.
So intermediate particles, it doesn't care.
And
So suppose
And actually, I know how that looks like. It's
suppose
just,
yeah.
so basically, you get some value which is not an max square, right? So basically, you move your plane in some direction, but.
Yeah,
That's-
but
that's fine.
it's since all he is caring about the initial particle and the final
Final.
particle. That's it.
Yeah.
And in between there could be a virtual particle, real particle.
I don't
It
care
doesn't
about
matter.
this virtual particle in the cascade. I was just wondering if your initial state is not a particle, but some process with some random p square.
No, here he is assuming initial state is a particle. So that's why, like a particle.
Now I know that if you have a virtual initial state, then you just don't get an x
Yeah,
squared,
yeah.
you get some other value,
Mhm.
and that's still a plane that comes
Yeah, within this geometry.
Okay.
I mean, the intermediate state is not going to change the kinematics of the final state particles. After you put in the matrix element, then you're going to get something different. But we are trying to not to look at the matrix element at all. Okay, so let's talk about the phase space volume element in terms of these quantities. So here's the product of our EXIJs. So interestingly, we get these delta functions, and this delta for this is valid for n greater than or equal to 4. So at least for body final state. You can go through a cascade decay, or doesn't matter. You can just mathematically study a direct time body decay. But this is the volume element. So this delta 4 again is the inferior n dimension and larger than 4. That's the principal minor of that matrix. And these delta phi's up to delta n are all principal minors up to a sign. And this delta n is the determinant of the matrix. Okay, and we also have this overall energy conserving hyperplane in this case, like we did have for the 3-body case. So now you can complain that there's way too many variables here, which is right. Normally, if you think about just a scalar interaction, n by the final state, we have 3n vectors, right? Minus 4 for the overall formal momentum conservation, and 3-dimensional rotation with symmetry. There is 3 n minus 7 essential variables. But over here we have n times n minus 1 with 2 variables. But these delta functions, although it looks like there isn't enough of them, actually takes care of the number of dimensions. Okay, let's talk about some decay chains. If you just think about four-body decays right now, here's all the possible chains going through either 2 or 3-body cascade decays. So if you imagine one of the final state particles to be invisible, first of all, you don't want to put it over here, and you can just combine these two into one particle. It must be at the end of the chain, and at the same time, it cannot be in this anchor topology because if it's over there, and this can be combined into one particle, and that effectively becomes 2 plus 2. So there's only 2 possibilities basically, 2 plus 3 and 2 plus 2. And there isn't much difference between 2 plus 3 and 3 plus 2. Okay, so let's study 2 plus 2 topology. Here's the cascade decay, and label the unknown masses x, y, z, and 1, 2, 3, 4. And 4 will be invisible. And same thing, similar thing for the 2 plus 3 topology. Okay, so we want to construct a likelihood. So again, we are dealing with minimum number of events. So we want to use all the events and combine them to get a good measurement of the mass. So we can have a combined likelihood by just multiplying each likelihood for each event. And we're going to have a mass hypothesis, which we show it tilde over here. And that's going to give us an understanding of the, how well those masses fit the events. Now, to test this, we generate just 3 experiments. We take just 10 events, measure the masses, and then take another set of 10 events, measure the masses, and so on. And we assume an ideal world to make things easier, just to see what you can do best in terms of measuring the masses. So no detectors, meaning we assume we always catch the correct combinatorics and no background, just the same.
So in real experiment, how will you generate the likelihoods? You are doing the likelihoods based on Monte Carlo, right?
Right, yeah.
So in a real experiment, how will you have the likelihood?
I mean, you'll have a sample of events, you can set of signal events, and this likelihood is going to take, you'll see it in a moment, it's going to take like numbers from each event, and then it's going to give you a likelihood for that combination.
So how do you weight those events? Do you use n squared, or
Do
you have a underlying theory and give you n squared?
Well, we are trying to avoid that, but we have to do something, so we're just going to choose scalar.
You just look at
Scalar
you just look at momenta. You don't weight them with n squared.
Well, we will, but it's going to be just scalars, decay into scalars. Just to make things simpler. No,
Because I'm trying to understand. So let's say you have a bunch of events, and all these events, because they come from a very big phase space, so you get different events with different points in your phase space. So let's say you have 2 points in your phase space. So how do you determine this one looks like more like a 2 plus 2 plus 2, and the other one looks more like a 2 plus 3? So,
I mean, okay.
Because you have to use
that reminds me one thing I forgot. We assume all the events come from the correct decay chain.
Correct combinator.
Let's
So that's
simplify everything,
Correct combinator.
and also correct decay chain. So let's assume everything to be perfect, and then you can relax those
sorry,
later.
I didn't remember that wrong. So you first you have assumption that you are expecting something like a 2 plus 2, and then you test whether those events look like a 2 plus 2 plus 2. And it's not. I was wondering whether you're doing the other way. It's,
Yeah,
you have
I'll
some
show that
events
too.
and determine which combinatorics fits
Yes,
better.
I'll show that too.
Oh,
So you start with a 2 plus 2 plus 2. What happens if you apply 2 plus 3 analysis on it? Yeah, but yeah. Okay, so again, so if you think about the matrix element and the phase space part, the boundary of the phase space comes from the masses. But what happens inside that boundary is related to m squared. But the boundary itself is just determined by the masses involved in the decay. It doesn't depend on the matrix element itself. So we can then just start with this fully differential decay bit in terms of xij's. And we can write that d gamma in terms of d phi, and write that in terms of our xij coordinates. We also want to normalize this, not to bias some part of the phase space. So you can add m1 over gamma x on it. And also, so we are just dealing with scalars, and we do everything in the narrow-fit approximation. So then the only thing that you get in m squared is just coupling squares, and then propagators, scalar propagators, which become pi over m gamma. Okay. So you can imagine dialing down the couplings to smaller and smaller values to make this thing work, and to go into the narrow-fit approximation region. And if you are doing that, at the end, couplings will disappear. And if you are dialing them down, they should disappear. And if you actually take these gammas and calculate them with correct masses and replace these gammas in this expression, they cancel out, and this is what you get at the end as the likelihood function.
So by saying correct masses, do you assume that you know the mass of the intermediate states?
No, we don't know any of them.
And then
So
the
x, y,
value-
z, and 4 are not. No.
Oh, okay.
We only know 1, 2, 3. We assume actually, as you can see from these expressions, to be massless. That's standard model like stuff. Okay, these expressions come from those gammas, or decay bits. And this part comes from this four-dimensional or four-body phase space written in terms of this xij coordinates. And if you remember from our discussion, delta 4 equals 0 for the four-dimensional four-body and higher number of particles in the final state defines you the boundary of the phase space. So delta 4 equals 0 is where the boundary of the phase space is. And there's a singularity over here. We see that also in the phase space Fallen element, of course. So in a sense, if you look at a phase space in terms of these coordinates, xij's, there's an enhancement of events on the boundary. So hopefully we are capturing that. Okay, I'm gonna show the result at the end. We'll do some numerical study of how this works, but it works pretty well. So I just want to now generalize this for different set of decay chains. So the idea was just to have 1 over gamma and write this fully differential decay bit in terms of xij coordinates. But what happens, let's say, there are invisible particles, as we assumed. So some of the xij's are not going to be observable. Right? So those ones we integrate them out because we cannot see them. So for 2 plus 2 plus 2, we have 1, 4, 2, 4, 3, 4. We cannot measure, so we actually integrated them out from the expression. But but one thing I forgot to put here is the delta functions coming from the propagators in the narrow root approximation. So we had actually 3 delta functions and 3 integrals. Those integrals kill the delta functions. So here's the general result. You can just write down a recipe for this, and each time you see a vertex like this, you just plug in this over here. These functions are just in this form. If you want to do just 2-body and 3-body, you just have these 2 type of functions, and you insert the vertex energy conservation at each vertex. Even the first one, x equal to, let's say, 1 plus y, will satisfy that. And finally, you integrate over all the invisible stuff. You have all these delta functions, very complicated delta functions, and it's delta 4, and some constants. So if you count the number of delta functions over here, so each vertex, as I said, will bring a delta function. If MB is the number of vertices, there will be MB. And there is this extra delta functions coming from the way we write the phase space volume element. That's n-4. But there's only n-1 integrals. So at some point, things are going to get a little different. Okay, some of these delta functions can be evaluated in this, using this expression, using Gram determinants. And before going into the final results, I'm going to just make a couple of definitions. We all know this triangle function or Kelvin function we get in the 2-body decay, or it's a 3-particle kinematic function. You also have a 4-particle kinematic function where you get it in the 3-body decay. You can just generalize this. And actually, the nice thing is this lambda gives you the area of a triangle. This G gives you volume of a tetrahedron. And you can just generalize it in this form as a so-called Cayley-Manning determinant. And this will give a generalized ruler of a simplex in n-1 dimension. But we will need this to specify the final result. And I'm going to write down the final likelihood in this form. Okay, everything comes out very nicely. There's a normalization factor all the time that doesn't depend on the mass hypothesis. It doesn't depend on any of mx and y and z and so on. There's the functional part that depends on the mass hypothesis. And there's a theta function in all of them, which will eliminate some part of the mass hypothesis space and get rid of large volume of it. Okay, let's go to 2 plus 2 plus 2. Again, applying that, as I said, there's 3 delta functions for each vertex and 3 integrals. And the integral is simple. You can write down the final expression in terms of these lambda 5s. So the interesting thing here is both this domain, the part of the likelihood which defines the domain of the likelihood function, depends on the event itself and the mass hypothesis. And at the same time, the functional part also depends on the mass hypothesis and the numbers you will get from the event. But for example, if you look at 2 plus 3 topology, so first 2-body decay and 3-body decay, in this case, here's what happens. Since we have only 2 vertices, we only have 2 delta functions, but 3 integrals. 2 of them will kill these 2 delta functions. And we need to complete one more integral. This delta 4, or 1 over square root of delta 4, is quadratic in that variable. So it's going to be a not so difficult integral at the end. But the interesting thing is the final result, the domain depends on the mass hypothesis, right? But the functional part of the likelihood, the part actually will maximize, does not depend on the individual, like the values you will get from the event itself. Doesn't depend on the these M1, M1, 2, 3s, and so on. So you can first find the domain where you live in the likelihood space, and then you can maximize the likelihood and find the maximum likelihood results. And you can do this for a number of topologies. And here's some results. So 2 plus 3, 3 plus 3, 2 plus 2 plus 2, 2 plus 2 plus 3, and it's 100 and 1,000 events. And the correct masses are 100, 350, and 500. So for example, 2 plus 2 plus 2 works very well with even the 100 events. You get ridiculous precision. Of course, if you include detector resolution, combinatorics, background, this will change, but just to see the ideal case, it does very well. And similarly, 2 plus 2 plus 3 does also very well. But interestingly, 2 plus 3 and 3 plus 3 don't do that well, as you can see from the uncertainties in the final masses. And the reason is just what I explained a minute ago, that the domain and the functional part doesn't depend on the event itself. So in a sense, you don't get that much information, but you get a lot of information in the 2 plus 2 plus 2 case. And here's the histograms of the masses. You observe as pink ones with 100 events and blue ones with 1,000 events. And you can see the difference over here. This is 2 plus 3, and over here is 2 plus 2 plus 2. This is much more peaked and different shape actually compared to 2 plus 3. And so here's the reason. If you make a table like this, number of vertices versus number of final state particles, we are not interested with these. These are just the vertices, 2 and 3, but we are interested in this region. Over here, you have, in your likelihood definition, you have equal number of delta functions and integration variables. But over there you have one less delta function. So you have, in a sense, less information over here, which makes the likelihood work worse. But over there you have more information. And if you recall from polynomial methods, I mentioned if you have a long cascade, you can actually solve the event in solve the masses in a couple of events. That corresponds to this region. Okay? And so we can just calculate the number of delta functions remaining in the likelihood. Over here we had one less. Here we have equal number of deltas. Over there we'll have one more delta than the number of variables. So in a sense, after we are done with the integrals, we have one delta function remaining in the likelihood. That's going to be a delta 5. You can just play around a little bit, remove that delta 5 from the direct delta function. And in a sense, your likelihood will be just delta 5. And in a couple of events, those delta 5s will give you intersecting surfaces and will give you all the masses. So we cover, in a sense, the polynomial methods by just doing this likelihood method. But we do better than the polynomial method, which doesn't work over in this region because there is not enough constraints to solve the system. Okay, here's the wrong mass hypothesis. So topology, correct topology is 2 plus 2 plus 2. Assume 2 plus 2 plus 2, and you solve very well. Now topology is 2 plus 2 plus 2, and you assume 2 plus 3. You can still work out some numbers. It's not going to be as good as the correct topology. But here's the interesting thing, obviously, 2 plus 3 topology is not going to be fitted well with the 2 plus 2 plus 2 hypothesis. So it just, after looking 10 events, you conclude that the correct topology is not 2 plus 2 plus 2. But the other way around doesn't work that way. Okay, as I mentioned before, we can talk about the likelihood function, domain of the likelihood function, and the actual function part that you maximize. So here's what happens. This is the unknown mass space. So for 2 plus 3 topology, it's x, y, and 4. These are the unknown masses. So if you make a plot of the remaining part of the allowed space, after you use 1 event, 2 event, and so on, as you can see, the allowed region shrinks very fast. And this red point is the correct actual mass. And after just a couple of events, you converge very fast to that point. Okay, so what is next? Addition of spin correlations. Of course, we want to do the same thing and see what happens if you can see the spin assignments in the chain. There's a couple of possibilities for, let's say, a four-way final state. And there are some works done on that subject, but I think the simultaneous measurement of mass and spin is not very much explored. This paper assumes the masses are known to measure the spin, for example. And effect of combinatorics, obviously, if you have lots of particles, it's not easy to always get the correct combinatorics, but you can sum over all possible combinations and define your likelihood in that way. And what happens in the case of pair production and decay, we assume there's only one invisible particle, and we did not use any missing transverse momentum. If we have pair production, we can maybe add some more information and add finite width, detector simulating, and of course background. But I think this was a good start. And conclusions. So it looks like we might be in trouble in the sense that we're not going to have too many new physics events at the end of the LHC's lifetime. So we really need to focus on methods of extracting the largest amount of information from them. And it looks like if you look at the full dimensionality of the phase space, you actually collect more information than a collection of one-dimensional projections, which is just edge and endpoint methods. And well, I didn't show you the comparison, but the likelihood method does better than the edge and endpoint. Way better, for example, in 2 plus 2 plus 2, but still very much better in 2 plus 3 topologies. Thank you.
Can you go back to one slide before?
I'm sorry, I need like 20 decibel more to be able to.
Yeah. Can I get that